Welcome back, everyone, to McCall Science Enrichment Online. Today's experiment is titled, Why Are the Poles of Earth and Mars Cold? Not all the planets in our solar system have poles that are cold with ice. And today we're going to determine, or try to determine, why that is true. Now, the first thing we need to focus on today are our materials, and then we'll go into our procedure. Now, we are using today the instructions that I've been posted for the past week. These instructions are titled slanted, which is another word for tilted, and that word we'll get into in just a bit. Now, I've changed this experiment a little bit away from the original instructions so that it can be seen more in a three-dimensional sense. So the first materials that we'll need today are, we have here some sharp bamboo skewers. If you choose to do this experiment at home, be very, very careful because the points of those skewers are very dangerous and very sharp and very strong. We also have today, very important, probably the most important items, we have some markers which are bound by rubber bands to hold them together. I chose to use markers that were round in shape, and I chose the biggest markers that I could today so that you can clearly see the marks that these markers make, okay? And the next thing we need today is 4 or 5 pieces of plain white paper. Make sure that they don't have folds or creases. They're nice and flat. The next item today is, I have used today a common, rather large, not necessarily totally round, red grapefruit. And I've written, of course, the word Mars across the outer skin of that grapefruit, okay? Now, the final item that we'll need today is a cantaloupe. Yes, a cantaloupe. Now, this is a melon. It has a stem connection here. You'll notice that this cantaloupe right now is wider than it is tall. I could have used the cantaloupe like this, but that would have meant that the cantaloupe would have been taller than it is wide. I chose to use it like this because if this cantaloupe is going to represent our Earth, you may notice in some of your reading that the Earth is wider than it is tall. And that's because when the Earth rotates on its axis, the water that covers 2/3 of the surface of our Earth tends to expand outwards. So our Earth actually bulges widthwise left to right. Okay, so those are our materials for today, and now let's go into our procedures. So for today's experiment, the first 2 vocabulary words that we're going to address are the words planets and axis. Now, our fruits today, our grapefruit here and our cantaloupe melon here, are representing 2 of the planets in our solar system. They're representing Mars and Earth. Now, I have taken the liberty of placing one of these bamboo skewers through each of these 2 model planets. You'll see that these bamboo skewers pierce the bottom and the top portions of these planets. Now, I did that to show the axis. Now, the axis of each planet is the point in which the planet rotates. Now, it just so happens that Mars will rotate at this point and this point. These axes are imaginary points, but the planets do rotate at these points. As the planet rotates, the axes do not move. Now, my little grapefruit here is sliding down my bamboo axes, but as Mars rotates, the planet will rotate, but this point will not move and this point will not move. And it's almost as if they do have a bamboo skewer piercing the planet so that they can rotate. Now, the same is true for the planet Earth. This is a rather heavy cantaloupe, so I'm going to have to kind of rotate it like this. Now, I'm showing you the axis as the Earth rotates this way. It's almost as if the Earth does have this little pole or this axis, this skewer shoved through it so that as the Earth rotates, the axis points don't move. And that's very important for today's lesson. All right, as we mentioned previously, both Mars and Earth rotate on their axis. They don't rotate up and down. They do something else. And there's probably a reason for that. It's thought that at some point in their history, both Mars and Earth, probably while they were forming, were hit by some very, very large object. So as Mars rotates on its axis and then also rotates around the sun, it's not rotating straight up and down. If it did, Mars would not have any ice accumulated at this pole and this pole. It would also have the same weather over the whole planet. It wouldn't have seasons. It wouldn't have different weather between the hemispheres. But that's not the case. Mars does have seasons. Mars does have ice at this pole and this pole. And it doesn't rotate straight up and down. No, it rotates at a tilt, which means that about 20 degrees Mars is tilted like this. So when it rotates at a bit of a slant. That's why today's experiment is subtitled Slanted. All right. Now the same holds true for Earth. Much like Mars, Earth does not rotate straight up and down. It too probably was hit by something in Earth's past that made it tilt on its axis. So when Earth rotates, it's rotating at a tilt of about 20 degrees away from the sun. That means that Earth, like Mars, has seasons between its hemispheres. It's also not the same temperature from north and south, east and west. The parts of the Earth over the course of a solar year change. It has seasons. So both Earth and Mars have tilts. And that has effects on the poles of each of these two planets. Okay, so the answer to our ice question for both planets is going to be answered by these two markers. Now I've taken a simple permanent black marker. I've tied the two of them together with two rubber bands so they hold together. I only have to pick them up once and they stay together. But as I've put them together, there's a distance between these 2 points here, okay? Now the markers are side by side. They're both at the same length. They're both in the same relative position. They're just tied together. And that gives me a distance between this marker and this marker. Now these markers are meant to represent the beams of sunlight, the rays of sunlight that are coming from the sun from that direction. So the sunlight is coming in straight towards these two planets. Now the same answer applies to both planets. Right around the mid part of each of these two planets would be the equator. Now Mars' equator would be about halfway between its two poles, about where my thumb is. Now you can see that as the sunlight comes in, both of those points are going to touch the equator at the same time, and they're going to be exactly this distance apart. All right? Now the same holds true for the Earth. Even though the Earth is tilted, the equator of the Earth is about where my thumb is. As those beams of sunlight come in, they're both going to hit the equator in about this spot, that distance apart. Now, I've left two little marks here with the markers on, well, just one. If you want to, and you're doing this at home, you can mark your cantaloupe, or you can mark whatever fruit you're using, whatever model, okay? I do like to take these markers as they are, this distance apart, and actually draw on them on a flat piece of paper, because you'll get more of an idea of the true distance between these two. So I'm going to take these markers and I'm going to use them and draw them on flat paper. Hang on just a sec. So we have our two markers here. Our markers are arranged to show how two beams of sunlight traveling in a straight line strike the equator area of both Mars and the Earth. Notice that these 2 points are exactly one above the other. They're totally lined up. Now all I have to do is take my markers, pick them up, and I'm going to drag them this way to show you the distance between these two markers. Let's draw it just like this. Those two markers are this far apart, indicating the distance between two possible rays of sunlight striking our planets at the equator. Okay, now at this point, I've arranged my markers so that one marker has its point farther this way than the marker here. Now sunlight travels very quickly, so these two markers are still representing two beams of sunlight that are hitting the Earth and the Mars pretty much at the same time. But you'll notice at the poles of Earth, the Earth has quite a curve along its top portion. It's not like it's at the equator where both beams of light are striking the equator just a short distance apart. As these two beams actually touch the Earth, they're touching the Earth where there's a tilt. The tilt is here at this pole. As these beams of light touch the Earth where the tilt occurs, they're touching down, say, here. Okay? Now, I'm kind of pushing a little bit and I'm marking my Earth model. Now, I hope that I put a mark on these. There it is. Now, the distance between these two points of light should be larger than the distance between these two points of light. Why? Because as the Earth tilts away from the sun, those two beams of light at the tilt strike farther apart, as is shown by these two markers. Now the same holds true for Mars. If I had the beams of light at the equator, these markers would be at the same length and the same point, and those two beams of light would touch closer together here at the equator. But again, Mars is tilted away from the sun at this pole. So these two beams of light are striking like, they're striking like this. I'll see if I can get a mark here and here. So as I leave marks for those two beams of light here at this tilted pole, I'm getting this distance. Now I'm also going to take these two markers arranged just like this to accommodate for the tilt, and I'm going to draw a line with these two markers showing this new tilted distance. Hang on. Okay, here's what these markers look like and how they're arranged to imitate the way that the sunlight, traveling in a straight line, strikes the tilted poles of both of our planets, Mars and Earth. Now, one of these points is slightly ahead of the other, okay? And there's going to be a distance between these two at a diagonal. Now, I'm simply going to take our markers and I'm going to lay them on the paper like this, and I am going to draw parallel lines. Here we go. Now, these are the lines with a distance between here and here for the sunlight hitting our tilted poles. Okay, so here we have our two pieces of paper. One piece of paper indicates the distance between two beams of light with the tilt of the Earth taken into consideration at one of the poles, and this shows the distance between two beams of light taken at the equator of the Earth and Mars. All right, so what we're looking at is the distance between this line, to this line, and this line. All right, now my hypothesis is that because my markers were farther apart, that this distance from here to here will be greater than this distance from here to here. And actually, it's very subtle. I've taken both of these pieces of paper and I have cut a diagonal here in the end. So what I'm going to do is I'm going to lay the diagonal for the tilted piece of paper, and I'm going to lay it over the equator piece of paper. And what I'm going to do is this. And it's kind of tricky. I'm going to line up this point here. Looks pretty good. Now, if both of these common points in both test strips line up at that point there, this line, which is for the tilted beams, is longer than this line for the equator beams. Now, I know you're going to say to me, Mr. Pruteski, that's not a very big difference. They're not that much bigger. No, it's not. But these are just two beams of light in one point in time. Remember that the sun, given the halves of the Earth, is constantly shining, okay? The point being this: in a year's time, for the Earth and Mars to rotate around the sun, I have this much less sunlight falling on the poles of our Earth. I have more distance between the beams of sunlight, which means that across this hemisphere of the Earth, across that curve, the beams are farther apart. So for the whole distance on the poles of the Earth and Mars, I have fewer beams of light. At the equator, the beams of light are closer together, So at the equator, I have beams of light that are closer together. So I've got more beams of light. And essentially what happens is this. At the equators of both Mars and Earth, I get more sunlight. That's why it's hotter there. Now, over the course of a solar year for both planets, their equators get 2.5 times the sunlight that the poles do. Because they get 2.5 times the solar radiation, they're not only hotter, but there's more solar radiation to go around at those points. At the poles of both Mars and Earth, there's less sunlight, there's less solar radiation, which means that it's colder. So cold, in fact, that ice is allowed to form at those poles. So this is a very, very simple test. It's very subtle. It involves measuring. You can be far more exact than I can. I know you can. But this talks about how sunlight is affected by the Earth and Mars tilting away from the sun. Not only does it provide less solar radiation at the poles than it does at the equator, but it also requires that both planets have ice at both of their poles and seasons, changes in seasons and temperature. That's our experiment for today. I hope you get a chance to try this at home. Please, 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 only use things that you have at school. Don't spend your hard-earned money. Be safe, and I'll see you next time on McCall Science and Enrichment Online. See you then. Bye.